Okay, hi, good morning everyone. This is the second video, and this second video we're going to look through the structured questions in the wave worksheet. Okay, even though they look very long, but actually they are super easy, so don't worry too much. Okay, so without further ado, let's look at the first question. Figure 1 shows a girl operating a radio control car. The transmitter emits radio waves that are detected by the model car. The frequency of the radio waves is 27 megahertz. M for mega, right? Hz for the unit hertz, megahertz. Okay, ayo, my pen, so cannot see. Okay, anyway, right. State the speed of the radio waves as they travel through the air. So the speed of the radio wave in n, or more like speed of any like light waves, light rays, radio wave, gamma ray, and so on. They have the constant speed called the 3.0 times 10 to the power of 8. Alright, so this actually means 3 and then 8 zeros behind. Alright, so 300 million meters per second. Alright, so explain what is meant by the frequency. By the frequency is 27 megahertz. So what is actually going on is, the first thing is, what is frequency? Right, what is frequency of a wave? Now, if you were to remember like frequency and period, they are like the opposite of each other. The period is the time for one wave. Okay, period is the time for one wave, and if we number of time, the amount of time for one wave, for frequency it will be the amount of wave for 1 second. So it's like a reverse. So frequency is number of wave in 1 second. So, and then what does 27 megahertz means? 27 megahertz, if we were to write out the full amount, is 27, right? Mega means million, so we got 6 zeros behind. Okay, so it will be 27 million hertz. Right, so what is meant by this frequency is 27 million hertz, meaning frequency, the number of waves, the number of complete waves in 1 second is, then 27 megahertz means 27 million hertz. Or okay, the number of complete wave in 1 second is 27 million. So there are 27 million waves, complete waves in 1 second. Okay, so like that, right? So it's just that first mark for your frequency, second mark for the megahertz. All right, so that's question 1. Now question 2. This diagram represents a transverse wave. You have your displacement of the particles, so meaning there's a center line. The particles either move up or down, correct? Transverse wave. Okay, and this is the distance from the origin, and then all these are your particles. Okay, let's, and then OPSPT or OPQR, STU. Okay, so yeah, these few places. Okay, now, so which of the following lengths is equal to the amplitude of the wave? Underline the correct answer. So if you look at this, all right, which one is the amplitude? So amplitude actually is the vertical distance maximum displacement. Right, so amplitude, okay, over here, this is your maximum displacement. If you were to look at the graph, which axis is your displacement? Right, which axis is the displacement? The vertical axis. So meaning it's the maximum distance from the center. So what is this actually? It will be either S to this point or this point to T, correct? Right, so but we don't have a letter here, so the best we can do is MO or ON. So our answer is MO, right? MO or ON. Okay, if they have the ON. Alright, number 2, which of the following lengths is equal to one wavelength of the wave? Underline the correct answer. So one wavelength over here, very simple. So it's either O to Q, P to R, S to U, then that's about it. So 3 possible answers. Okay, OQ, SU, PR. So which one is there? OQ, right? Or PR or SU. Okay, or yeah, so these 3 answers. Okay, if they have then you can note down. Okay, now give one example of a transverse wave. Light waves, right? Light waves, radio waves, microwave, gamma wave, and so on. Okay, so that is question 1. Okay, section B, question 1. Now this one, we'll be talking about sound wave. Sound wave is a longitudinal wave. This question we'll cover in next chapter, so this one we'll just skip. Right, don't worry about it. We skip for this one first. We'll revisit this next chapter. Sketch a graph of pressure against time, also next chapter. So can skip first. Okay, state how the graph will be different. Also never mind, can skip first. Okay, number 2, explain by reference to the ripples on the water the meaning of the term transverse wave. State what is being transferred by the transverse waves on the water surface. Alright, so actually what does transverse wave means? Okay, and we have to talk about the ripples on the water. Okay, we have to mention, someone bring in the ripples on the water into our explanation. So first and foremost, the transverse wave, the key word to remember for your transverse wave is it must be perpendicular. But which two things are perpendicular? Right? Which two things are perpendicular? It must be the movement of the wave. So the direction of the wave. Okay, direction of the wave. Right? And the direction of the vibration of the molecule. So the vibration. Okay, the wave direction and the vibration must be perpendicular. So these two keywords must be there. Alright, so and when you want to, okay, so the first thing, let us write this. Okay, so transverse wave is a wave where it's direction of travel is perpendicular to to the direction of the vibration of the particles. Okay, so this is actually a long ass statement, but what you can do is you don't have to remember so long, just remember the keyword and then elaborate more on the keyword. Now then, with reference to ripples on the water, so what does this mean actually? So meaning the ripple on the water is the one that move the ripple on the water, as the ripple of the water travel right from one end to the other end, the water molecules will be what you call this, vibrate perpendicularly to it. So yeah, so what is this actually? So as the water ripples travel, right, the water particles, water molecules actually, since you have learned chemistry, right, so the water molecules move perpendicular to it. Okay, so the up down motion. So as the water ripple move this way, the particle will move up and down. Okay, so next, state what is being transferred by the wave. So the wave transfer energy but not matter. So the waves transfer energy. Okay, so much for 3 marks. Okay, but not matter. So meaning the wave molecules don't move, but the energy of the wave will move from left to right. Okay, all right, so here the next question, there are 2 types of waves, transverse and longitudinal. Give an example of each type. So longitudinal, only one kind of wave, which is your sound wave. Or actually got one more, is the slinky, but slinky depends, that slinky can do both. Okay, now but transverse wave, you can do your light wave, your rope wave, water wave technically has both, light, rope, your radio wave, right, microwave, so yeah, gamma wave, and so on and so forth. Okay, so yeah, you can think of a few examples for this one. Number 2, state the difference in terms of particle motion between a transverse and a longitudinal wave. So here we want to state the difference. Okay, the difference of the particle motion between a transverse and a longitudinal wave. So the particle, how does it move in a transverse wave? The keyword is perpendicular. Longitudinal wave, the keyword is parallel, right? So parallel to what? Parallel to the direction, parallel to the wave direction. Okay, so you can say that the particles, right, particles in a transverse wave move perpendicularly to the wave direction. Okay, then the difference is whereas the longitudinal wave moves, or the particles move parallel, okay, to the wave direction. Okay, so yeah, there you go. Okay, there you go. Okay, so that's this one. Okay, B. The diagram represents a wave. On the diagram, show the wavelength of the wave and the amplitude of the wave. So we have to draw. So when we draw, make sure we use pencil. Okay, wavelength. Okay, so wavelength, so wavelength meaning 2 points, successive two crests or two successive throws, or from origin to origin, from middle point to middle point, and so on. So many answers, but I'm just going to play safe, and I'm just going to draw from crest to crest because it's the easiest to draw, like this. Okay, and I'm just going to label it wavelength and use pencil when you do this. Number 2, amplitude of the wave. Amplitude is the maximum displacement, so from the center point is the vertical distance above. So this one is what we call the amplitude, right, like this. Okay, wavelength, amplitude. Okay, now wavelength, other answers of wavelength, it can be this, right? It can be like this. If in the middle, if you want to be adventurous, it also can be this, right, like this. It also can be all the way down in the so many answers, many version of answers. Alright, as long as you try to draw to one wavelength. Okay, alright, so there you go, 3B. Okay, 2 more pages to go. Alright, 3C, state in the words the equation which relates the speed or the velocity of a wave to the wavelength and frequency. So this one, the velocity v is equals to f lambda, but we want the words. So here the speed of wave, right, is equals to f frequency, right, times wavelength lambda. Okay, like that. Okay, D. The lines in the following diagram represent wave crests. So all these are crests, and these are the wave fronts for the crest. Okay, viewed on the surface of a ripple tank. So first crest, second crest, and so on. Alright, so very quickly we can straight away identify something first. So if these are crest to crest to crest to crest to crest to crest, how many complete waves are there? Okay, we have 1, 2, 3, 4, 5. So we got 5 complete wave. So we can write down here 5 complete wave. Right, 5 complete wave is 15 cm. Right, so what's the length for one complete wave? Okay, so what's the length for one complete wave? Just 3 cm divided by 5. Okay, right, so we need this information later. Okay, and then what is the frequency of the wave? If 5 seconds ago crest R occupied the position now by crest W, so from here to here, right, from here to here, okay, so R traveled from here all the way to here. Alright, 5 seconds ago crest R is here. Now 5 seconds later crest R is here at the second point. Alright, so what is the frequency of the wave? So actually R from here to here, so it traveled a wave of 5 distance, correct? So meaning 5 complete wave, right? 5 complete wave take 5 seconds, right? So travel 5 waves distance, right, take 5 seconds. Alright, so we are looking for the frequency of the wave. So frequency meaning the number of wave in 1 second. So in 1 second, How many wave? Divide by 5. So we got one complete wave. Okay, so what is this? One complete wave in 1 second, meaning this is just 1.0 hertz, like that. Okay, okay. Number 2, calculate the speed of the wave in the ripple tank. So we've got wavelength, we got frequency, wavelength, frequency. So we can actually use V equals to F lambda. So speed of the wave, F is here 1.0 hertz, wavelength is 3 cm. So the speed of the wave is just 3.0 meter per second, not cm per second. Okay, take note, yeah, cm per second. Okay, now, or if you want to play safe, just change this 3 cm right to meters. So this will be 0.03 meters. Okay, so this will be 1.0 hertz to 0.03 meters. So this will be equal to 0.0302 SF and meter per second. Alright, so this one you just be careful. If they never give, if they give the meter per second, the unit down there, you might need to change this distance first. Okay, so tricky, be careful. Number 4. Right, the diagram shows a wave moving along the spring by pushing and pulling one end. So it's just pushing and pulling here. So this vibration, right, is just like pushing and pulling here. So what type of wave is shown in this diagram? Because the movement is parallel to the wave direction, so this is actually our longitudinal wave. Okay, longitudinal wave. Now, name a naturally occurring example. So this one, only one example so far, it is sound. Okay, so what do the letters R and C represent? Okay, so this one is actually next chapter, but don't worry, I'll just give you first. R represents rarefaction. C represents compression. Okay, rarefaction and compression. Okay, so this is number 4. Number 3, don't worry first. Okay, so next, part B, the diagram show a wave moving along a string by moving one end up and down. So up and down movement, the fixed end, and then you get a string. What type of wave is this? This is actually what we call a transverse wave. Transverse wave. Okay, so name a naturally occurring example, light rays, light wave. Okay, now on the diagram, mark the position of one wavelength. Why to mark? Oh, okay, mark the position on one wavelength. So it can be here, like what we mentioned. One wavelength is just the length of one complete wave. So from crest to the next crest. Okay, 2 successive crests. So this is wavelength. Alright. Or it can be okay, it can be like throw to throw, crest to crest, throw to throw. Okay. Or it also can be like, middle point to middle point. Or if you don't want middle point to middle point, you can actually do like here, like somewhere in the middle of this one. Also can. Okay, so entirely up to you. But just play safe lah, huh? So the easier one is just up there. Okay, so that's all for waves. Okay, I hope this chapter, there's a lot of heavy terms, but don't worry too much. You just let it be. Okay, just leave it be. You just need to get used to the just let your fears aside, just get used to the terms, because this chapter is actually very, very, very easy to manage, so don't worry too much. Okay, it's just a lot of terms, a lot of new words, but the concept is very easy. Okay, so I hope you take your time, try to read back and remember what you learned in this chapter. Right, we can borrow the concept from here in the next chapter, sound. Okay, so that's all for I have for you today. Have a good day ahead. Bye bye.